Friends, let's get to the next lecture. In this lecture, we will try to see the basic law of thermodynamics. So, when we talk about thermodynamics, there is only heat, work, energy. So, it keeps going around the same thing. Maybe you look into a cycle, or you will look into a law, or you will look into some applications. So, fundamentally it goes around it, because we have understood what is state property, path function, then we looked into cycles, right, and then we looked into PV diagram, TS diagram. So, that is all it is. So, it goes just around it, but little bit more of understanding at every level. So, in this lecture we will go through little bit deeper on work and heat transfer. First we will see work transfer, followed by it will be heat transfer, then it will be latent heat transfer. If time permits, some problems we will try to see during the lecture, or in the tutorials we will try to have some problems solved. In any thermodynamics process, a system can undergo a change in its energy content. However, energy itself, you know very well, it can neither be created nor be destroyed. It can be converted from one form to the another. So, this is the principle of conservation of energy, which is otherwise called as first law of thermodynamics. The total energy of an isolated system remains constant, but it can change form or move from one body to the another. For example, I have a hot body, I am touching it with a cold body. There can be a difference in temperature. They will try to find out the gradient, and with respect to time it tries to normalize, right, both become to the same temperature. So, there are only two basic ways in which the energy can be exchanged between system and surrounding. It can be either work or it can be heat. Heat and work are only recognized at the boundaries of the system. Boundaries of the system, surrounding, system, boundary. This is boundary, right, recognized at the boundary of the system during a process in which the energy is exchanged. It can be ice kept here surrounding at ambient temperature. So, you can see at the boundary what is happening. Work transfer. In thermodynamics, work is a form of energy interaction between a system and its surrounding. When there is a mechanical force acting across the boundary, typically resulting in a macroscopic motion. Friends, work is not a property of a system. It cannot be stored or contained. Instead, it can only recognized during the process of energy transfer. Now, you should be very clearly distinction, you will see energy can neither be created nor be destroyed. This is a principle of conservation of energy. Now, let us look at work. Work is not a property of a system. It cannot be stored or contained. Instead, it can only be recognized during the process of energy transfer. The direction of energy transfer matter, the direction in which the energy transfer happens. If the system does work on the surrounding, such as expanding a gas to push piston, it is considered as positive work. When the system does something and throws it into the surrounding, so it is said as positive work. If the system does work on the surrounding, AC unit does something and give a comfort to the surrounding. So, the system does work on the surrounding, such as expanding a gas to push a piston, it is considered as positive work. If the surrounding to do work on the system, when it is on the system, such as compressing a gas, the work is said to be considered as negative work. Now, friends, you can go back and see your PV diagram or your TS diagram. You can see where positive work happens and where negative work happens. In thermodynamics, the work typically refers to a boundary work. The energy transfer results from volume change due to pressure, such as gas expanding in a piston. The energy transfer resulting from volume change due to pressure. You compress, pressure, gas heat, gas expands, such as gas expanding a piston cylinder device. Other form of work includes electrical work, shaft work and spring work. Spring work is what yesterday I was trying to talk about, spring balance. You have this thing and then you have a hook. So, you have a hook wherein which you put the weight, right. There is a graduation, this graduation reduces. So, other form of work include electrical work, shaft work and spring work. Thermodynamic work is considered as positive when done by a system and negative when done on the system. So, I have compared expansion and compression. It is a path function, which means its magnitude depends on the specific way the process is carried out and not merely initial and final stage. Please note down this point. It is a path function, work transfer is a path function, which means its magnitude depends on a specific way the process is carried out or not merely on the initial and final stages of the system. The thermodynamic work is often associated with the change in volume of the system due to pressure and it is commonly referred as boundary work. So, it is predominantly here is compression expansion. The thermodynamics work is often associated with a change in volume of a system due to pressure. Work transfer. Work is a path function. This means that amount of work done depends not only on the initial and final stage of the system, but also on a specific process or path that taken to go from one state to the other state. Work is always measured in terms of joules. So, you have a hot rod. So, you can see this portion is hot, this portion there is a transit and this portion is cold. I will say intermediate and this is hot, right. So, this means that the amount of work done depends not only on the initial stage and the final stage of the system, but also the specific process, the path with which it is going, taken to go from one state to the another is also defined as work in a path function. When it is infinitism work or differential form, when a system undergoes a very small change in volume, which is dV, and the pressure at the boundary is P exit, the infinitesimal amount of work delta W done by the system is defined as work done is equal to pressure into volume, right. So, this is del, this is P exit and this is dV, right. So, delta W is the change in work done, external pressure P exit and delta V is the change in volume. This form assumes that the process is quasi-static. Static is permanent, quasi-static is in between, right, and dynamic is the other extreme. This form assumes the process is quasi-static, that is, it proceeds infinitely slow so that the system remains in equilibrium at every stage. When a system remains in equilibrium at every stage, it is called as quasi-static. It proceeds infinitely slow so that the system remains in equilibrium at every stage. So, slow moving is quasi-static. So, this is infinitesimal work. The other one is integrated form. Integrated form is for a finite volume change, when the volume is very small, right, when the finite volume change happens. To calculate the total work done over a change in volume from V1 to V2, we integrate W, which is volume from V1 to V2 times P exit into dV. So, now you see the difference. When it is very small, it is delta work is equal to P exit into delta V. When it is a finite change in volume, W equal to integration V1 to V2 P exit into dV. To calculate the total work done over a volume change from V1 to V2, we integrate the differential volume. This equation represents the area under the PV curve. What is PV curve? We studied PV curve can be like this, something like this, right? You can take PV curve. I am just giving a very idealistic case or just an example. So, the area under the curve in a PV diagram. So, this is called as a integrated form for a finite volume change. So, this is what you can see here. So, when the work done on gas, the work done by the gas, right. So, if it is work done on the gas, dV is less than 0. When dV is greater than 0, you see this. So, minus P dV is equal to W when work is greater than 0. When work is less than 0, we get this form. Where did this negative come from? If you refer to my previous lecture, you will see where did this negative come from. Okay. So, this diagram clearly says what is the work done on the gas, what is the work done by the gas. When is dV less than 0? When is dV greater than 0? If V2 is greater than V1, it is expansion. So, the work will be greater than 0. The system does positive work on the surrounding. When V2 is less than V1, it is compression. So, the work done will be less than 0. The surrounding do work on the system. So, when I try to go back and look into that integrated form, P1 to P2, right. So, this is P versus V. So, P1, P2 are the pressures initial and final. So, if the pressure is very high and if it is trying to expand with respect to volume, the pressure falls down, the volume gets expanded. So, it is called as expansion. So, the work is equal to area integral V1 to V2 P times dV, which is greater than 0. When it goes into compression, from V1 to V2 it goes. So, the pressure from P1 to P2 it goes. So, the work which is done is equal to area. So, then you get V1 to V2 PVD P with a delta V small is always less than 0. So, if you want to represent it in C, we can try to see that P you try to draw V1 V2. So, from P constant pressure, it expands by volume, pressure is constant. So, then the work is equal to area, which can be represented as P V2 minus V1. So, when we try to have a constant pressure, right. So, the work transfer. So, it is interesting, we saw V2 greater than V1, V2 less than V1, right. Then we are now trying to see constant pressure process. What is constant pressure process? You might know it is isobaric. In an isobaric process, the pressure remains constant throughout the entire volume change. W is equal to P times V2 minus V1, where work done is W, pressure is constant, V1 minus V2 is initial final or final minus initial. So, when we try to plot PV diagram, so V in the x axis is delta V is the change. So, we can try to take V1, V2. So, delta V is the change between V1 to V2 and then the pressure which is maintained constant A to B. So, the area is going to be P times delta V, which is equal to the work. Delta V is V2 minus V1. So, this is what it is, V2 minus V1. When we have a isothermal process, what is isothermal process? The temperature is constant. So, how can I represent temperature constant in PV diagram? You cannot. So, what you do is you have a TS diagram. In this diagram, temperature will be constant. It can be T1 to T2, right? In TS diagram, where S is entropy, T is temperature. In PV diagram, when it is drawn in isothermal process, it with a constant temperature, we represent it like this. So, an isothermal process occurs at a constant temperature, which implies that the internal energy of an ideal gas remains constant. Delta U is constant. Internal energy is represented as U. Therefore, any heat added to the system is entirely converted into work. The heat which is added to the system is entirely converted into work. So, the formula for this is going to be W equal to nRT natural logarithm of V2 by V1. What is N? N is the number of moles of the gas, where R is the universal gas constant, T is the absolute temperature, and V2, V1 are the volumes. Okay. So, now you see for isothermal process, how do you represent the work formula? If you go back, you see for isobaric, how do you represent the work, right? So, when you look at the pressure versus volume diagram, when you are trying to move from initial to final, so then nRT, which is mole constant temperature, into natural logarithm of Vf by Vi. So, it is this. So, this is the area under the curve, where in which the work is greater than 0. Now, let us try to take adiabatic process and see the work transfer. In adiabatic, there is no heat exchange. So, you remember adiabatic Q, right? In an adiabatic process, no heat is transferred to or from the system. So, it is only two things, you push into the system or get it from the system. So, there is no heat transfer. This means all the changes in the internal energy are done to work. If you look at the previous one, you can see there the heat added to the system is entirely converted into work. If you see here, all the changes in the internal energy are due to work alone. So, here it can be represented as gamma as a W equal to P2 V2 minus P1 V1 divided by 1 minus gamma. This gamma can be represented as Cp by Cv, which is the heat capacity ratio, where P, V and T are pressure, volume and temperature. So, this is P1 V1 T1, there is a delta exchange, right. So, it becomes P2 V2 T2, right. When there is a temperature constant, then T2 becomes both T are equal. So, when it goes from P1 V1 T1, when it goes expand by delta x, this is what it is. And when we try to plot it with a PV diagram, we see there is a curve. When it is expanded, moves from here to here, there is a expansion which is happening. So, this area which falls below this curve is called as area enclosed, right. So, here the work transfer is represented by this way. So, for adiabatic process we have seen, for isothermal process we have seen, and for a constant pressure also we have seen. So, friends, you have three processes. For a constant pressure process, how do you calculate the work? For isothermal process, how do you calculate the work? And for adiabatic process, how do you calculate the work? Now, let us try to understand for a polytropic process. Polytropic process is generalized case described by PV n equal to a constant, where n becomes 0 when you put isobaric, when n becomes 1 if you put isothermal, when n equal to gamma is adiabatic, when n equal to infinite is a constant volume process, which is called as isochronic process. So, the work formula for n which is not equal to 1. So, when it is not equal to 1, it can be 0, it can be gamma, it can be infinite. So, then it is represented as work is equal to P2 V2 minus P1 V1 divided by 1 minus n. What is n? N is these values which you take, and if you go in the previous n, it talks about the number of moles of the gas, right. So, here if n is not equal to 1, So, then we represent it like this, or we would like to redefine this properly, move left and right and all. So, work done is equal to Nr T2 minus T1 divided by 1 minus N. It is almost the same. You see here, how did we get it? So, you can derive it and then get Nr T2 minus T1. So, this is for a polytropic process. When isochronic process, when the work volume PV equal to PV diagram and the volume is constant. So, volume is constant, it goes like this. So, there is no change in pressure, volume constant. Whatever you play, volume is constant. So, isochronic process, the constant volume process, the work formula is W equal to 0. So, since dV is equal to 0, the boundary does not move and no work is done. So, any heat added changes the internal energy, but not the mechanical state. So, it is pressure versus volume. So, it is a constant volume process. This is how you draw. So, isochronic process. So, the work done will be equal to 0. So, if you look into it, so everywhere the work done you can try to find out. So, this is the area enclosed, right. So, in isochronic process, work done will be 0, no work is done. So, this is a table of comparison for various processes, various conditions, expressions, and what are the real time examples. So, isobaric process, which is a constant pressure process, we will have the formula for work done is equal to P V2 minus V1. So, it is used in boiling water at atmospheric pressure. You keep pan, pour water in it, heat it from the bottom, right. The boiling water at the atmospheric pressure. So, V2 minus V1. Isothermal process, which is a constant thermal process, which is W equal to nRT natural logarithm V2 by V1. So, here constant temperature, the temperature is maintained constant. So, gas expansion with heat exchanges follows this isothermal process. When we talk about adiabatic process, there is no heat exchange. So, the formula is W is equal to P2 V2 minus P1 V1 divided by 1 minus gamma. So, what is gamma? Cp by Cv. So, it is used in rapid air compression in engines. When you compress engines, IC engines and all, rapid air compression happens. Polytropic is PVN equal to a constant, where this gamma is replaced by an N. So, it is used in compressor, real gas systems. We always use polytropic process. Process type is polytropic, condition is this, expression is this, and real time example. When it is isochronic process, it is constant volume. So, where W is equal to 0. So, the gas in sealed rigid container, if it is there, is a typical example for isochronic process. Isochronic process you saw here, there is no work done by the system. So, here any heat added changes the internal energy, but not the mechanical state. So, till now what we saw was only work transfer. So, I told you in the beginning itself, here if you see, there are only two basic states. One is work transfer, the other one is heat transfer. We have studied about the work transfer. Now, let us move to heat transfer. Heat is a fundamental concept in thermodynamics and referred to energy transfer between two systems or a system and its surrounding due to its temperature difference is heat. It is a fundamental concept, right. So, the energy transfer between one system to the other system when they are close by, or system and the surrounding. Unlike internal energy, which is a property of a system, heat is not a property, but a process quantity. Friends, please try to understand the difference between property of a system and a process quantity. Heat is energy in transit caused by a temperature gradient. When there is a hot body, cold body, there is a connect. Then we will try to see heat is a energy in transit. Heat is a energy in transit caused by temperature gradient. It flows spontaneously from a body at a higher temperature to a body of a lower temperature, hot, cold. The heat transfer continues until the thermal equilibrium is reached. Once the thermal equilibrium is reached, then it is all stay safe, nothing more. right. So, heat is a thermodynamic concept, it is a energy transfer between system and surrounding, right. It is due to temperature difference. So, it is a process quantity. These are important terminologies which you should know. Unlike work which involves mechanical or electrical interaction, heat is an invisible, spontaneous energy transfer that flows from region of higher temperature to a lower temperature. Friends, look at the difference between work. Unlike work which involves in mechanical or electrical, heat is invisible. You cannot see the heat. Invisible, spontaneous energy transfer. It is like a radiation, spontaneous energy transfer that flows from a region of a higher temperature to a lower temperature. It is not a property of a system and cannot be stored or contained. Rather, it exists only during a process in which the temperature gradient are present, right. The symbol for heat is Q typically. The differential form is delta Q and the unit will always be joules. In thermodynamic sign conversion, when Q is greater than 0, when heat enters the system, it is endothermic process. When Q is less than 0, the heat leaves the system, which is exothermic process. So, endothermic, exothermic. Exothermic means heat is rejected, heat leaves the system, heat enters the system, right. Endothermic. So, there are two sign conversions. So, when we talk about heat transfer, the energy is transferred between the Earth's surface and the atmosphere in a variety of ways, which is including radiation, conduction and convection. Convection, there can be forced convection also. So, here you keep a pan filled with water, you heat it from the bottom. So, there is from the heat there is radiation. Because of this heat there is a conduction, because when you touch the top side there is a heat which is there, that is conduction, and when the handles become hot condition, so it is conduction. And what happens inside this circle, which is a convection. So, convection happens because there is a difference in temperature. This difference in temperature tries to bring this swirling action. So, that is called as convection. The modes of heat transfer, there are three different types. So, the heat can be transferred in three primary ways. One is conduction. The heat transfer through a direct molecular collision and vibration within the solid or between a solid in contact without any bulk movement of the material is called as conduction, right, without any bulk movement. So, if you see this vibration, it is interesting. When you look at microwave oven which is used, microwave when it is when you switch on a microwave and you have a vessel wherein which you filled with water and then you have some rice particles or something, right. So, now what is happening, as and when the microwave comes, they try to interact with water, and the water they have dipole molecules. These dipole molecules rattle and vibrate. When they rattle and vibrate, they create friction. Friction is converted into heat and that is how it boils. So, why I am trying to tell you this story is because vibration in molecular collision and vibration is quite common when heat is there. So, there are bonds, they will hold to each other. There is lot of heat, and now this fellow will have a small instability, they will start vibrating. So, that is what it is. So, you have a metal rod which is a good conductor, the heat is applied from one end. So, now the so because of the vibration of the particles, the heat gets moved from one point to the other. So, the vibration particles plumbing against each other, right, pumping against each other or vibrating with a bond which is restricted, they vibrate. So, then what happens, the energy flow happens from the hot end to a cold end, that is by conduction. What is radiation? The transfer of heat through electromagnetic waves, infrared radiation, which can occur even through a vacuum without any media, is radiation. So, radiation does not need a medium. It can happen through a vacuum also. So, sun radiates heat on the earth, radiation. The transfer of heat through electromagnetic waves. So, from here also if you see electromagnetic waves, heat, transfer of heat through electromagnetic waves which can occur even through a vacuum without any medium is radiation. The most interesting part is convection. Convection is nothing but a heat transfer by the movement of fluid. The fluid can be liquid, the fluid can be gas, where warmer portion of the fluid rises, cold portion sinks down, thus creating a flow reaction. There is a flow. So, cold molecules come down, hot molecules go up. So, it does not go just like that. So, when it moves like a whirl, right, and this can be larger or smaller. So, the heat transfer by the movement of media. So, suppose you have a room, inside a room you put a fan, right, and you have a hot, very hot heat radiation which is coming. Assume a cold winter day. In a cold winter day, there is a radiator which is kept inside your room and then it radiates. Then you want to uniformly distribute the radiation inside the room. So, what you do is you put a fan on. So, that tries to move the hot air and try to push it towards the cold air. Cold air gets circulated and it comes back. So, that is convection. So, the most important terminology in heat is always specific heat. It is a fundamental property of matter that describes the substance ability to absorb heat. If the specific heat is high, it can absorb more heat, an object or a material with a high specific heat. It is defined as amount of heat required to raise a temperature of 1 unit mass of a substance by 1 degree Celsius or 1 Kelvin without any change in the phase is called as specific heat. So, heat divided by unit degree. The concept is essential in thermodynamics because it determines how different materials respond to addition or removal of heat and play a critical role in thermal energy calculation, heating and cooling process and the design of a thermal system. So, the amount of heat required to raise a temperature of a unit mass substance by 1 degree is specific heat. The specific heat is Cp for a solid, and a liquid is Cp equal to Cv equal to C. Whereas, for a gas, Cp is the specific heat capacity at constant pressure, Cv is specific heat capacity at constant volume, right, Cp, Cv. For a solid liquid, this Cp equal to Cv equal to C. So, there is another term which is called as latent heat. It is the amount of heat transferred to cause a phase change. Amount of heat required to raise the temperature unit mass of a substance by 1 degree without a change in phase, specific heat. It is the amount of heat transfer to cause a phase change is latent heat. The unit is joules. Sometimes it is kilojoules per kg for a specific latent heat. This represents the energy need to break or form molecular bond. So, latent heat is very much required to break or form a molecular bond. So, if you want to machine polymer, so we will always try to break the molecular bonds, right. So, that is a latent heat is very, very important. So, the latent heat transfer can again have 3 classifications, like you see here Cp, Cv, specific heat capacity at constant pressure, specific heat capacity at constant volume. So, latent heat is latent heat of fusion, latent heat of vaporization, latent heat of sublimation. Latent heat transfer. The latent heat transfer, as I told, has 3 categories: LF, LV, LS. So, the latent heat is represented as joules per kg and it comes in several forms depending upon the phase change involved. So, heat of fusion is amount of heat required to convert a unit mass of a solid to liquid is latent heat of fusion. When we do casting, when we do melting of ice, when the ice at the North Pole gets melted, it is latent heat of fusion. The amount of heat required to convert a unit mass of solid into a liquid at a constant temperature and pressure is given. So, for a latent heat of fusion of water is 334,000 joule per kg. When we try to talk about latent heat of vapor, it is the amount of heat required to convert a unit mass from a liquid into a vapor. From solid into a liquid, it is heat of fusion. From liquid into a vapor, it is called as latent heat of vaporization, or vice versa at a constant temperature and pressure. The water for LV for water is 2260,000 joules per kg. Watch out the numbers. Then latent heat of sublimation, the energy required for a solid to directly convert into a gas without passing through a liquid phase is sublimation. The process requires most energy per unit mass since it combines latent heat of fusion and vaporization. So, it is very simple. You have solid phase, you have a liquid phase, you have a gaseous phase. Solid to liquid is LF. Liquid to gas is LV, right. From here to here you go, it is LF plus LV, that is all. Okay. So, latent heat of fusion, latent heat of vaporization and latent heat of sublimation. So, friends, in this lecture, we try to see the basic difference between heat and work. We saw the definition, we saw when is the work said positive, when is the work said negative in thermodynamics. We saw work is a path function. We saw various types of work transfer. We saw various types of heat transfer. Then we tried to see specific heat and latent heat. Okay. So, now let us try to have some examples or exercise for ourselves. Take camphor. So, solid camphor and it gets converted into gas. Try to see what time it takes to get converted from a solid to gas, or you can try to take naphthalene ball, very small, have a large surface area, very small volume. You see what is the time it takes to get transferred. Then you try to take ice and then try to see a normal ice at room temperature, how much time does it take to get converted into a liquid, complete liquid, right. Now, with this time factor you have noted, so now you go back to your latent heat of fusion, latent heat of vaporization, latent heat of sublimation and try to understand time against this, so that you try to have a feel for it. And again, if you note down, I have reported it with huge values with respect to kgs. So, whatever you have taken may be few grams. From that, if you try to transfer and find out what is the latent heat of fusion, then that will be nice exercise for you. So, we also saw in this convection radiation, which we discussed in last lecture also, and we did some, I gave you some examples. So, now in the same example, can we try to have a fan which rotates at certain RPM? Okay, let us do that exercise once again. You take 1 liter pan and fill it up with water, try to heat it, try to reduce the water to half of it, note down the time. Now, you try to allow it to come to room temperature. Next, what you do is, for the same setup, when you reduce from 1 to half, then you try to blow air on top of it. Now, see how much time does it require to come to room temperature. Now, what are you trying to do? You are forcing some media and trying to improve the convection and see what is the influence of forced air on it. The third one, what we will do is, we try to take the same 1 liter to bring it to half a liter and then try to keep this pan inside one more beaker of water, wherein which there the temperature of the water is 25 degrees. See how much time will it take to come down to room temperature inside the vessel. So, when you do this exercise, you will try to understand what is the influence of the surrounding on your convection, conduction and radiation. So, while preparing this lecture, we have used a lot of references. So, these are the references which are predominantly used. With that, I would like to complete this lecture. Thank you so much.